Okay, so my name is Hansang. I work for Citigroup, or Citi, and most of you heard this spiel before, so I have a couple teams that report to me. We do capacity planning, troubleshooting, and I also own the fault alerting and monitoring space at Citi. So when the routers misbehave, it sends out an alert. It goes to the systems that we have. And also, since we do the troubleshooting, and we're responsible for troubleshooting, we happen to be the biggest users of protocol analysis. So we own the appliances that do packet capture, and we do the design and certification of these products, and then we give them out to the regions for deployment. Okay. So again, you know, my email's on the. I think this is my email address. I'll correct it. I'll double check. But I kind of, as soon as I saw that, I said, "Is that my email address?" It's going to be on the Wireshark website. And just drop me a note saying more in-depth, less in-depth, because I can also split it out, right? I can actually say this is an in-depth presentation where we'll tackle 2 or 3 traces at most, and we'll deep dive. And the other ones I'll just keep doing quick and dirty. You know, here's a problem, here's how you recognize it, this is what you saw, and then move on to the next one. Okay? If you have any questions throughout the session, please let me know. With all these fans and everything, it's kind of hard for me to hear, so I'm already hard of hearing anyway. So you'll have to scream it out, and then I'll repeat the question for sake of the recording, and so let's get going. Oh, okay. Okay, thank you. So the first problem is internet is slow. So a user calls and says, internet is slow. My internet locked up. And that's the description that we got. So what do you do? I mean, it's the internet. Do you just punt? I'm sorry? And the point number 2 there is actually when you have presence in over 200 countries worldwide, getting a concrete description of the problem can sometimes be difficult, right? In general. This user happened to be in New York, so language wasn't a barrier. But you know, the report that came out said I was using the internet at 11:15 or so. My browser locked up, and it wouldn't work. I had to close it. A few minutes later, I came back, and it was working fine again. So the kind of problems that I hate the most: transient, intermittent, no rhyme or reason. But something caused me to investigate this a little bit further. Anybody guess what that might have been? Any guesses? CEO. Very close. He was 1 or 2 down from the CEO. So I said, all right, I'll take a look. But normally, these types of tickets get triaged through the help desk, and when they do come up, it's because a large number of users have reported issues at the same time. This was an individual user, but you know, 1 or 2 down from Vikram Pandit, so you know, bad career move to just ignore him, right? So the first thing we want to do is we want to take a look at the packet trace. Again, we got a sniffer out there. We said, let's turn on the capture and take a look. And this is what I got. So, what's the first thing that you see here? Again, remember my core emphasis constantly is pattern recognition, right? And this one, pretty easy. One direction. So now what do? Do you just throw this trace out? A lot of people might do that, but you'd be surprised how much information you can glean in a one-way trace. And sometimes you don't have the luxury of getting, especially what we talked about before in the earlier session, how you have asymmetric routes, right, redundant paths. The redundant path may actually go through a different building, and you may not have enough infrastructure to capture every point that you want. Sometimes you make do with what you have, right? And some of the things that I want to point out quickly is that 8080, you know, obviously it's a large corporation, and we have proxies like I'm sure almost all of you guys do. And as you look through this trace, every once in a while, you do see some two-way type traffic, okay? And I actually think I know why this is happening, but I didn't want to investigate, so I kind of moved on, but I have a hunch we have at layer 2 asymmetry with HSRP and MLS. So if you're curious about what that is, just go to Cisco and search asymmetry HSRP MLS, and you'll get a very nice description of what the problem is and why packets get flooded, etc. Okay? So that's not really my concern, not my focus. So what's the first thing that we can look at here? So here's the user. One of the things that we can look at is the acknowledgement number, right? So if we keep an eye on the acknowledgement number as we kind of scroll down here, when the server starts giving us packets, right? I come down here, here's port 80, I'm sending him something, right? And obviously I get traffic back in the other direction. So what can I do with this? Well, one of the first things I do, again, is this, right? This is muscle memory. Is this going to yield too much in this case? Maybe. But when you're only dealing with a one-sided packet trace, all of this is pretty much suspect, right? So I wouldn't spend too much time looking through this here. I do see some Windows update. Nothing really. Some duplicate acts, maybe. Am I going to be too concerned about it? Not really. Why? I got 99 here that's marked. So 99 events were flagged out of 5,800. Okay? So, yeah, it's sort of kind of is, but considering that the user said the browser locked up, remember, it wasn't slow. If it was slow, we can chalk it up to packet loss congestion. But if it locked up, something horrible must have happened. Okay? And again, we were lucky enough because the user said around 11:15 or so. So what do? I go to my handy-dandy configuration profile, bring up the absolute time, and let's just scroll down to 11:15. Here we are, right around 11:15. Now what? What do I normally do? I just scan. I go down, and I look for things to jump out at me, keeping in mind my time frame here. And this is exactly what I did. So I'm recreating what happened when we were troubleshooting this. And nothing really jumped out, except for every once in a while there's a pretty big delta. But again, when you're dealing with a website and the internet of a large corporation, these things don't necessarily trigger anything, right? Could be anything, who knows? So as we started looking at this, we said, there's really nothing here. And being that this person was a very important person in the city, I didn't want to go back and say, yeah, I didn't find anything, sorry, have a nice day. So we dug a little bit deeper, and I asked the folks that provided me the packet trace, what filter did you use? And they said, oh, we used it from this user on port 8080. And I said, well, that's too limited. Right? Because what happens in a TCP/IP communication? What can go wrong that would block traffic? I'm sorry? ICMP, port unreachables, okay? ICMPs can come from, but if I'm filtering on the anything to 192.168.1.1, I should be able to catch some of those. What else can? ARP, okay? So all of a sudden ARP gets confused. And 2 years ago, as a matter of fact, I had that exact scenario that I presented where the ARP table got corrupted by a misconfigured driver. What else can, kind of more high level, what can block communication from network converging back and forth? We would see some packet loss. I don't see that too much here. Something simple, remember, if you hear hooves beating, think horses, not zebras. I'm sorry? DNS. So I said, well, I don't see any DNS here, do you? Well, let's check. Handy dandy filter. Nothing. So I went back to the sniffer, and I re-downloaded the packet trace, and this is what I got. So let's scroll down to here, and let's scroll. Port 8080. Oh, there was something. Did you guys see that flash? Right? It happens that fast, but your eye can pick it up. So you go back, and what do we see? We see to our Anycast DNS address a query. And clearly this is work related because it's Evite. And then the person actually said I had some invitation that I had to answer, and it locked up on me. So what's wrong with this trace? Right here, we said stop, do not pass go. Something horribly went wrong. And what is it? In a large corporation, when you talk to the internet, what do you use? I'm sorry? Web filtering via proxy. So are end users supposed to query evite.com, google.com, amazon.com? Absolutely not. Right? Because in browsers, you have what's called a PAC file, proxy autoconfig file. And actually, if we scroll down here, we'll see references to the word WPAD, which is Web Proxy Automatic Detection, I believe. Right? And it's a way of browsers saying, hey, I need to talk to somebody outside of my organization. How do I know it's outside of my organization? Because my proxy PAC file told me. So in our PAC file, it lists all of our address space and our domain that you can directly query the internal DNS. Anything else, you talk to the proxy and let it worry about it. So the minute we saw this, what likely happened? We know it's broken because it's an outside .com address space, and the browser decided to query directly for evite.com. So what's the likely solution? What went wrong here? Anybody? Okay, the person could have changed the setting, but this is not a technical user, and it's also locked down. So they don't even have the option of changing it. Any other? PAC file got modified, possibly. We didn't see any PAC files being downloaded, and if you look through this trace later, you'll see that you'll see PAC files coming back down, which would have been a big clue. Unfortunately, life's full of disappointments, and I have no idea what happened here. Because think about this: if our proxy configuration lost its mind, that's one thing. If our software deployment system that we use to push out patches happened to be pushing out a new IE update for the user, lost its mind, that's one thing. But if a browser or website can reach into my browser config and change the proxy, that's a huge, huge problem, right? Because any website can then say, come to me, right, and I'll take care of it for you. Talk about man in the middle, right? So we looked at it. We did see some evidence of...
Is that the actual DNS server you expect?
Yeah, it was the actual, yeah. So from an IP standpoint, it's the right Anycast DNS, but proxy was confused. I mean, the browser was confused. So we chalked it up to they were pushing out a new update, and they probably forgot to fill that proxy configuration section, right? So somebody, somewhere, forgot to check off deploy Internet Explorer, deploy PAC file setting. And if you forget to check that, this is what would have happened, okay? So that's sometimes I don't have all the answers up here, so we'll leave this one at that. Okay, so I kind of start out slow, and then we ramp up a little bit. So it'll get progressively more interesting. This one is the application is timing out. This was actually a big production system. They were about to go live. As they ramped up on to do stress tests with some corporate and federal guidelines and audit requirements behind it, obviously had a lot of high visibility. As they scaled up the testing, the application throughput and reporting went down. Right? So they called us and said, something's wrong with the network. And of course I said, something's wrong with your application, let's take a look, right? So we did talk to the developer, and they said, we have these logs, and it tells us exactly when the database is unavailable. And they called the database vendor, and the database vendor said, oh, it's your network problem. You can't talk to the database server, so clearly it's a network problem. Talk to your network guys, which they did. So we took a look at it, and we opened up the packet trace. And so this is a typical trace of, so what do we do first? The first thing we do always is TCP. And what do we see? Windows Update. Do we care about Windows Update for the most part? Not really. We do care when it's Windows 0, right? 0 Windows is very different than Windows Update. But when I see a lot of Windows Update, it also tells me they might be moving a lot of data. and people are having to kind of go down and catch up, go down and catch up. They just don't go very down or all the way down, right? So I know that the communication didn't stop, so okay, so it's not really a communication problem or a Windows problem. What else could be wrong? Oh, I'm sorry. So the other thing that I do is, out of habit, is this. I always want to see how many TCP connections an application is opening, because that's an indication that it's either very efficient or very inefficient. Okay? The reason why HTTP 1.0 was so slow, one of the reasons, was that every object required a new TCP session to be downloaded. You have 50 pictures, requires 50 TCP connections. Waste of resources, waste of round trip. Right? TCP, setting up TCP costs money in terms of time. So when I saw this, I said, wow, there are 226 TCP connections in a pretty short duration. So Blue's Clues, light bulb goes off and says, and I say, well, let's take a look at this because this might be a problem. So clear this. We'll go to Statistics, Conversations, and we'll look at the TCP. And again, all we're doing is looking at top talkers and anything that jumps out. And what jumps out here as I scroll down the screen? This is a conversation. Very, very small, if anything at all. So if you're going to come knocking on my door, come on in and have a conversation, and then you can leave. In this case, it's more like, and then you run away. And then you go to the door. Who is it? Nobody's there. Close the door. Again, waste of resources, waste of time. So what do we do here? So we said, all right, give us your application log that said the database is not available. And they came back and said, I forgot what they said. I didn't put it in here. They said around 5:31, approximately 5:31 p.m., they had a problem. Okay. So let's go to, so I'm right around there, right? 5:31 they said. So let's scroll down and do what we do, which is just scroll down and look. What's going on here? Anything? Did anybody see anything? I'm sorry? We saw some resets, right? So right away we said, okay, there are resets going on. What else could be going on here? Using different ports? Same ports being utilized again and again. That could be a problem. More resets. More resets. More resets. So we know that resets are a bad thing unless you're using IE, in which case they tear down SSL sessions with a reset, right? So when you're troubleshooting a web, don't jump to conclusions about, oh, it's a reset, it's a bad thing. It's not necessarily a bad thing, okay? So as we scroll down here and scroll up and we go to the exact time of the problem, something will jump out here. Actually, I'll cheat because I know what the problem is. So right around the time of the problem and resets happening just underneath this, we saw this. Anybody recognize this? What kind of query is this? That is a IPv6 address, not a quad A, single A record, right? So typically you'll see, for example, type is not A, address, AAAA, but this is definitely a link local IPv6 nomenclature. Okay? So I said, all right, well, is that a problem? Not really. Look at the response time of the queries coming back. 8 milliseconds. Is that good or bad? I don't know. Not too bad. Unless you scroll down and you start to think, well, there's a lot of them there. And how much time am I wasting by the time I go through this? And why did the system all of a sudden make these queries? Oh, and by the way, happened right about the time they said they had a problem. So you put 1 and 1 and 1 together, and we said, what's the problem? Right here we stopped and we said, I know what the problem is. What is it? Okay, so problem clearly is we have IPv6 going on when we're still IPv4. Okay, so that is a problem. That's a factual statement. But looking at this trace, looking at what the application guy said, the database was not available. I couldn't connect to the database. What's the likely problem, or what's the likely culprit here, just by looking at this trace? Exactly. So the application wanted to talk to this database and said, oh, let me do a DNS query, spent all this time doing IPv6 linked local, and by the time he finished doing this, the application said, the database is not available. Log it, move on. Okay? Then something else interesting happened, because if we follow one of these resets, and let's see if I get lucky. Sure enough, I did. I connect, and the reset happens. Why? Because the application said, I'm not going to listen to you. I waited. You didn't come to me. I'm going to close down the application, move on to a different port, and talk to somebody else. And because the application shut down, TCP said, I don't have anybody listening on that port. I'm going to reset the connection. Okay? It was actually a pretty simple trace if you factor in the problem description, the time, the fact that the application said database is not available, I could not connect, and then you see the DNS and time spent doing DNS, wasted time, right? And immediately you can piece all these things together and say, this was a problem. So how do you solve it? It's a Unix box. You just configure a netservices.conf file to say not IPv6 first, but v4. So the newer Unix boxes come with default setting of IPv6 first in the order of preference for buying. Okay? And so it sits there and says, well, IPv6, 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 nothing's happening, nothing's happening, nothing's happening. Eventually, it will kick into IPv4. But for this application with tight timing space, if they ran out of time and the application closed down. Okay? Any questions so far? No? Okay. So the next one is interesting, because I don't even have a packet trace to show you guys. But I thought it was interesting enough to present it here. NFS is slow. Is that the expected behavior for NFS v3? Yes, no, maybe? Anybody have problems with NFS and throughput when you're using TCP for v3? No? Nobody? Okay, well that's good. It turns out that NFS on some NFS servers and implementation can only use 32K block size. That's it. So it doesn't matter what your TCP window size is, it will transfer at 32 kilobyte chunks at a time. So if your data center is far away, your throughput is going to be limited to 32 kilobytes per round trip. You can never go beyond that unless you resort to some appliances, accelerators, move them closer, or use newer versions of NFS, or go back to UDP. Because obviously with UDP, round trip is not a factor. Okay? So what this team did was they spoke to the vendor. I almost said the vendor. But they spoke to the vendor. They got some recommendations. They said, oh, do some TCP offloading. Increase it to TCP offload engine here that you see to 14.480. Set your window size to something large. They chose 2600. And you should be fine. And in fact, it was worse. Throughput was not good at all. Why was that? Because, I'll give you the answer. It's a little tricky unless you think this, and again, this goes back to deep dive versus hit and run, right? The reason why this is no good is because your offload engine is yet another buffer outside of your TCP stack. So you have TCP buffering, then you have the offload engine buffering. Okay? And the buffer size is 14,000 something. You increase, MSS is 1460, 1448, sorry. It wasn't 1460 because we had some TCP options turned on. MSS is 1448. TCP offload engine is 10 times that number, which is 14480. But the window size on the NFS TCP stack is 26 something. So how many offload buffer space can you fit into a 26K window size? 1. Why? Why is it 1? Because in order for me to send 2 offload buffer size worth, I got to have 2 times 14480. If the offload engine and the TCP don't act and play nice, you've just limited your throughput to 14480, not 26280. Never mind 32K. Okay? So this was actually very clear when we charted in spreadsheets and whatnot, and let me see if I can actually show you that. I don't want to take too much time into it, but one of the ways we visualized this during our internal sessions was in fact, this is actually what I was talking about this morning about in-flight number of bytes and presenting it, because when you see it in unacknowledged data in flight with sequence numbers and timestamps, etc., you start to see a pattern of when am I acting, and when I act, how far have I received or sent, and you see these numbers pop up. Again, this is not important. I just wanted to show you that as you do analysis on TCP window sizes and data, and one of the key things that you have to look at is unacknowledged data that's outstanding. That's a big clue into how efficient or how inefficient you are. Okay? Because one of the things about TCP, and this is actually a nugget that I want everybody to remember, very simple. You cannot transfer more than 1 window size per round trip. That's it. Right? And that it's simple in concept, but sometimes people overlook it in troubleshooting. If your window size is 16 kilobytes, you can only transfer 16 kilobytes per round trip. That's it. Okay? So obviously, window size has a huge role to play in bulk transfer. Okay? The other lessons learned here, let TCP do its job. Let it buffer and control it with window size. As you start to get these offload engines and some other buffers, you get into a race condition where one buffer is waiting for the next buffer to empty or vice versa, and it's kind of tricky to catch. Okay, this one wasn't so tricky because I just said, give me all your settings. We looked at it. Immediately we saw this because we're used to looking for these things, and it jumped down and said, here's your problem. Turn it off. Increase your window size to 32K. 64K is a waste of time because NFS itself has a 32K limit. Okay, no reason to increase TCP to 64 when your application can only use 32K. Any questions so far? No? Okay. Next one. This is a very important business for us at Citi. Overseas users, Citrix. Sessions are slow, they're locking up, they're getting the disconnect message, and we have a carrier in the middle coming across the cloud. So obviously we said, it's the carrier's problem, because it's easy to say that. But we said, remember yesterday's session, when you have packet loss, chances are it's the network infrastructure that's the problem. More than any other type of problem, when you have packet loss, kind of look inside the house and take a look at the network before you start pointing the finger at the application guys. Okay, so let's take a look at this. And again, this is a case of, for the most part, one-way packet capture. And in this problem, I didn't go back in. I didn't have the luxury of going back in time to fix whatever was needed to be fixed. We were just starting to troubleshoot. So the first thing we do again, and do you think I can get a button right here that says TCP analysis flags so I can click on that? All right.
Yeah, that little yellow one down the bottom.
Oh, yeah. Oh, is that right?
Yeah, that's the easy button. Click on that little yellow button.
And it does the TCP analysis
Well,
flag?
it gives you your expert analysis all in a good.
Oh, okay. Oh, okay. Okay. But sometimes this throws me off, so but okay, I gotcha. All right, so let's do the analysis flag. Let me clear this. I think. All right, so let's take a look at, and I just took a 100,000 sample, and what do we see? Even though it's a one-way transmission, one-way packet, what jumps out at us as we're scrolling down here? Retransmissions. So retransmissions means I saw it twice. Is it due to some type of a spanning mistake where I duplicated every packet? No, because I only have 8,900 of them, not 50,000. Okay? I also see other evidence of packet loss, previous segment loss. So I got gaps in my packet train. So clearly, I have a congestion or packet loss issue. How do you go about troubleshooting this? Is there anything else more we can do at this point in time? Looking at it for a particular time? Okay, so what we're doing here is we're looking at, is it happening in bunches? Yeah. Right? Are they tightly grouped together? Could be. Let's take a look.
Where is this capture being done?
This capture was being done, I believe, on the near side as it entered city. Okay, so it had already gone through the carrier. So normally, there isn't actually much more you can look at or figure out from this packet trace, unless you're really, really good and you're thorough. And it's more about being thorough than being good, right? And so I went and keep in mind, this was Saturday morning at 6 o'clock. My boss calls me and says, "We got to solve this right now." And I said, "Send the packet trace. Let's take a look." We got on a call, and so I was being thorough, and I looked at the red-headed stepchild of protocol analysis, which is the IP header, just to see if there's anything there that can tell me in terms of IP ID, anything. Kind of grasping at last straws here, and I click on it. And instantly I said, oh, here's the problem. So I'm going to scroll down. Oops. I'm going to scroll down the packet. And the reason why I say open it and get used to looking at things is because your eyes will pick up on things instantaneously after you trained it to look at certain hot spots that typically come up again and again and again and again and again. As you stare intently at the screen, what jumps out? Anything? There we go. Expedited forwarding. So this is a Citrix transaction. Why is it using expedited forwarding? Because, well, actually you can, right? I mean, there's no rule that says you can't do it. But expedited forwarding is reserved typically for what? Voice traffic. And what do you do as network administrators and network engineers? What do you do with EF traffic on the routers, typically? You prioritize it, absolutely, you prioritize it, but you do something else. You rate limit it, because you don't want to be charged a lot of money when you go and you want to know that you stay within your 30 megabit pipe that you purchased, right? So, and you also don't want EF to go wild and consume every available bandwidth, starving out everything else. So typically, EF traffic is almost always rate limited. And I know that this site had a 30 meg budget for EF. And when I looked at the throughput, and you can actually kind of look at it from here, a little bit misleading because it's a small sample. But it says here average megabit is, wow, really small, right? It was a little higher when you see the full packet trace. So do I have a problem? Maybe. I don't know. But I do know it's not supposed to be EF, right? So I got lucky. And the reason why I got lucky is this packet trace, even though it's 100,000 packets, is really half a gig in a very short amount of time. That alone tells you how busy this server is and how many thin client servers it's hosting. Okay? And so in this trace, there are gobs and gobs and gobs of packets that you have to go through. How did I find it so quickly? I got lucky. I happened to be in the right place at the right time, because I'm certainly not going to look at the IP ID field of, you know, I don't know how many packets are in here, 700,000, 800,000, right? So one of the quick segue, again, this is a Wireshark conference, is if you have a graphical tool like Pilot, and I'll just spend just a few seconds here talking about it, the first thing that it'll tell you is, okay, I got a bandwidth megabit of 5.3 megabits per second, but not really, because if I look at it from a microburst standpoint, that 5 megabit turns into, any guesses before it finishes? More than 30? Let's take a look. Because remember, this is a small subsection of my trace, right? It's not the 5. I take that back. This is actually the 500 gig trace file. This is the full packet that it's crunching through right now. And it's going to tell me that I've reached, at microburst intervals, 600 megabits per second. Okay? Is that possible? So it depends. And the reason why it depends is, the more granular you calculate your throughput, the higher the number. Because, again, you can only have two states in utilization. 0, 100. Everybody else is lying. Because you can only have a packet on the wire or no packets on the wire. But obviously we can't do our capacity planning that way, so we start to look at it in bigger chunks of the wire, and then you start to average. Okay? So clearly there's bursting going on here, no question. And so then I said, all right, show me the DHCP, and I do this now out of habit, because A, it's easy, and B, I got burnt by so many times. And what do you see here? All of this is EF. Over 95% of this half gig trace file is EF, best effort, which is correct. But I got over 148 megabits worth of traffic, that's EF. Okay? So I really got lucky here. I happened to land on 5% of the population, and I happened to catch it. Okay? So again, the difference here is that regardless of the packet size, because I'm not opening a half a gig trace file in Wireshark and going through, but here visually I can instantly see, oh, this is a problem. And then I can right click here and drill down to my heart's content. Pick up conversation, IP, utilization, whatever you want, you can start to drill down. And this kind of, again, I wish I had used this, but at the time I just got lucky. Okay, sometimes you get your breaks and you move on. Okay, any questions about this one? Again, simple. Very, very simple if you know what to look for. Okay, and if I didn't open the red-headed stepchild of protocol analysis here, I would have missed it. And if I weren't in the right place, I would have missed it too. But so why did this happen? Okay, so a little embarrassing, so I didn't want to get into it because it's my domain, routing and switching. But it so happens that we were using TCP ranges to mark traffic. And older Cisco servers used the same port number, 2598. So if you were using CU, CM, CUXM, CUOM, SM, etc., version 3, 2598 was what Cisco wanted to use for its transport. Citrix, unbeknownst to me, at some point in time, decided reliable ICA sessions going to use 2598. So now I have overlap of TCP port numbers. Okay? So there's a lot of lessons learned here that we took out of at City. And obviously we had to do a quick triage and scan every single one of our routers to see if this old standard for QoS was in place or not. So that was the reason why. There was an access list that said if you're talking to port 2598, you're EF. Okay, simple as that. So then the next $1 million question is, if I'm overrunning EF, who's not complaining? The contact center people. And they always complain when they have bad voice quality. Right? And especially if you guys call up the credit card center and you get bad voice quality, don't email me. But it's probably a QoS issue, right? And so we were sitting there thinking, okay, this is great. We know that we maxed out the EFQ, 100%. We looked at it. We got the packet tracers to prove it. And we kept saying, but nobody called. Why is it that nobody in the contact center called? I'm sorry? I'm sorry. Okay. They couldn't do that much traffic. It's possible, but we have actually, this is a large contact center.
I think it's because it's UDP. Voice is
UDP? But even then, you're going to drop packets, right?
They just weren't getting calls, so they didn't think it was a problem?
They weren't getting calls, which is possible, but we have actually alerts when gateways and PGs go down. What else? It was actually rate limited to the queue. Whatever goes in that queue is fair games. So you're protected to go into that queue. Once you go into that EFQ, you duke it out with the rest of everybody else. Okay? Does that make sense? So if your pipe is this much, you have this much bandwidth, you carve out 30% of that for voice, and once you go in that voice queue, it's fair game. Normal TCP congestion control kicks in. Or in case of UDP, too bad, so sad, a packet got lost.
Did TCP back down because the voice is UDP?
So it's possible. TCP saw congestion and backed down, and UDP sneaked through the tunnel. But again, you're missing the most obvious answer. Again, you're looking for zebras, not the horse. So if that's the first thing I checked, actually, maybe they're not using this link. But when we put the sniffer there, they were. When do you need QoS? I'll give you a hint. When do you need QoS? When you have congestion. If you have large bandwidth, do you need QoS? Absolutely not. So where did my voice traffic go? Default queue. Because it was misconfigured yet again. Because if I'm expecting my voice traffic to be 2598 and it's not, how's it going to end up in the EFQ? It doesn't. It went to the default queue, and I had plenty of bandwidth in the default queue. So by happenstance, I blew out the EFQ, but thank goodness no voice traffic was traversing the voice queue. Okay? Right? It happens, right? Okay, so that was that, and again, sometimes it takes a little bit of luck to find the right answers. Okay, so the next one is time standpoint. We have about an hour, right? Okay. So this one is actually very interesting, Trace. Again, the actual problem is very simple, but the analysis part is what I want to walk you through. And this is the part where we're going to get a little bit more detail than what I've been presenting so far. This is a trading application where the log says there are delays in this trading floor that the systems cannot account for. And logically, and I don't blame them one bit, they said, oh, it must be the network. Because I've accounted for my application, right? We spent $200 million on this application monitoring system. I know it's right, and it can't account for this lost time. We're losing trades, we're losing business because the application log says you're always late. So where could it be if it's not the application? The network, right? Or I like to say the firewall. So there's a certain hierarchy of not blame game, but kind of, it's the router guys will point to the firewall guys will say it's not me, it's the proxy guys say it's not me, it's the application, and the circle of life continues. So this one, clearly though, we looked at the log and we said, yeah, you're right, you are timestamping it, and the packets must be getting lost. I don't know. So we took a sniffer and we looked at it. So we ruled out the usual suspects, which are what? When there's slowness in the network, what do we look for? Packet loss. What else? Latency, round trip latency, window size, right? But this is a trading applications, and trading applications tend not to send huge amounts of data. They send lots of data. A little bit different. So let's take a look. So immediately we see here a big delay, right? And it turns out this is an application level delay. There was nothing to worry about. So let's take a look. 192.168 is us. The 10 dot is the vendor. And I want to walk you through this trace, and we're going to go a little bit more detailed than I normally do, because the concepts are easy. The steps that you take to find these are not so easy. Okay? So the first thing we see here is what? All right, this is the start of the communication that I care about. First thing we check, TCP port number. I ask the app guy, is this your port number? Yeah, it is. Okay, we're good. Again, nothing worse than analyzing only to find out it's the wrong time or wrong packet trace file. So we know this is the right one. Okay, what happened here? So let's open up the TCP. And let's take a look. Describe to me what you see here that you should jump out at you as being somewhat abnormal, or at least not what you're used to seeing. Push, okay, so one observation is, which is also good, is push bit is set. Push bits are set when applications want to control TCP's behavior. They flush the buffer. They set the push bit saying, please send this up the stack when you get it. So push bits are good things to look for to say, oh, the application is trying to control the congestion or flow control instead of letting TCP do it. So that's the first thing that we notice. That's good. What else? 1 byte. It's sending 1 byte. That's not normal. So I asked him, is that normal? He said, yeah, it's normal. It means start a communication, synchronization message, etc. So I said, okay, that's fine. But when he said that, a light bulb went off. And I said, okay, stop right here. I know what the problem is. Nagel. And not just Nagel, but Nagel and delayed act. So what is Nagel and delayed act? I'll just spend it it's a very, very common problem, right? Nagel, the whole intention of Nagel is to do what? Buffer, right? So I don't want to send one packet. I want to see if I can kind of wait. Anybody in Rolf's class for wireless just now? It's the same concept. Let me just hang on to it a little bit, get some more data, and send it out in a big chunk, as opposed to single packets. So that was Nagel, and for the most part it works fine. But then there's a flip side to that story, right? And that's the delayed act. And what does the rule say about delayed act? I'm sorry? So wait 200 milliseconds. That's actually a variable. It can be 100, 150, can be configured, or sometimes it's hard-coded. 200 is a good number to look at because most systems, older systems especially, default to 200 millisecond timer. Because delayed act means I'm not going to acknowledge every single packet. And we actually have a big debate going on within our team. In a modern-day network, do I need to worry about delayed act? Is one extra packet in a conversation really that big deal? It's kind of like the spanning tree argument. Is one BPDU frame a big deal, and should we turn it off? Right? I mean, it's consuming anything. Who cares? In a modern day network, if I ACK every single packet, is that a bad thing? It's inefficient, but at some point I say, who cares? Right? I got megabits worth of bandwidth to play with, typically. So let's go through this trace and see what's happening. Oh, by the way, on delayed ACK, it also, the other rule says, acknowledge every other packet. So in other words, I get 2 packets. Oh, I'm sorry. I get 2 packets, acknowledge. Okay? And Nagel says, what? Send the packet, try to buffer it as much as you want until a timer goes off and send it on its way. All right? On the delayed ACK side, there's yet another story. It depends on which implementation you decided to follow. So some systems will consider full MSS as saying, okay, I got 2 full MSS, I can now acknowledge. Some systems will say, oh, it's not full MSS, you gave me 2 half-size packets, I'm still going to wait. A lot of Unix systems do that. Is it wrong? No, it's not. So again, we had a debate among our team that this is wrong behavior, so we went to Stevens. One guy went to Stevens, the other guy went to Comer. And when we read it, you could interpret it that way, right? So So okay, so but at least we knew enough to go back to the reference material and check, and we said, all right, it can go either way. We'll give them a pass on this one. So what happens to the next packet? What's significant about this packet? So this packet said it sent 1 byte, and the sequence number, next expected sequence number should be 70, right? I started at 69. I sent 1 byte, so the next sequence number is going to be 70. The acknowledgement for this packet should be 70, which it is. But look at the delta, right? It's delayed. And why is it delayed? Because he's following the rules of Nagel and delayed ACK. I got a small packet, never mind 1 or 2, I only got 1 packet. So you don't even pass the 2-packet test regardless of packet size. So now I have to wait. And I'm going to wait, and sometime later I'm going to acknowledge you. That does what to this guy? The client then does what? He sends 67. But how come the delta here is small?
As soon as that comes in, you can settle that.
Yeah. As soon as the ACK comes in and there are no unacknowledged data, I can send it out. Okay? So because I got the ACK saying, yeah, I'm good, he said, all right, you're good, I'm going to send the next batch out. And I've buffered up to 67 so far. Now, the next one is what? So here we have sequence number 70 plus 67, next sequence number 137. The next packet, for the first thing we check, acknowledgement number 137. We're good. But look at the delay. 8 milliseconds. Why is that? What's the difference between this guy and this guy? Here, he waited 200 plus milliseconds to acknowledge the previous packet that we sent. Here, he sent it in 8 milliseconds. Why? Couple of, I heard over here. He has data to send. If you look at the data length here, it's 87. Delayed ACK only applies to what I call naked ACKs. Naked ACKs meaning I have absolutely no data. I'm just acknowledging you that I got some packet from you at some point in time. So these naked ACKs follow the rules of Nagel, okay, or delayed ACK. When you have data to send, you don't have to wait. You can go. Okay? So here, so at this point in time, the acknowledgement number is 137. Then we get the next packet, and we get an acknowledgement. Why? Why did this packet come about? I'm sorry? He's acknowledging the packet that the vendor sent to us, and why did it take him this long to do it? Because he had no data to send, he didn't have 2 packets, so he has to wait for a timer to go off. Okay? So there's a lot of differences going on here, and this is why I like this trace. So let's kind of recap a little bit. Delayed ACK says, I have to have at least 2 packets from you before I immediately acknowledge. It could be 2 full-size packets, it could be 2 less than full-size packets. Depends on operating system and implementation. So the first test is, do I have 2 packets from you? Yes or no? Yes, I acknowledge. No, I'm going to wait for my timer to kick off. Then I acknowledge you. But when I get a packet from you, and immediately right after that, I have data coming from my stack. If the application wants me to send something, I don't have to wait. The whole point of piggybacking an ACK is when I have data to send, as long as I'm sending the data, go ahead and send the acknowledgement number as well, right? Don't just send the data and then send another acknowledgement immediately after or when the timer goes off. So the whole idea of ACKs, acknowledgement number, is you're kind of carpooling. If you have data that needs to go out, throw the ACK number there and send it on its way. Okay? So the difference here is that when I and this throws a lot of people off, right? And some of the junior staff on my team said, no, this isn't Nagel, this is something else, because look at this guy. he acknowledged me 8 milliseconds later. So it can't be Nagel, right? And then we said, no. You're conflicting two different things and turning it into the same story, right? Delayed acts apply to naked acts. Doesn't apply when the system has data to send. Okay? Is that kind of clear? So even though that's very simple concept, when you look at a packet trace, all of these things have to be going through your mind. Is this a naked act? Yes. Delayed act comes into play. Look for it. If there's data with that packet, throw a delayed act out the door. There is no delayed act because I have something to send. Okay? Key difference, but very easy to miss. Then, what's the deal with packet number 11? Yeah, it's application slowness. We saw one earlier, and this is doing some type of house cleaning. Okay? And then we start the cycle again. I'm ready. This is kind of like a start of field delimiter type conversation. He says, okay, but I had to wait for you. And why isn't it exactly 200? Because these timers go off all the time. You'd go insane keeping track of all the timers that are kicking off. So timers are going off. Sometimes you may hit 200 milliseconds. As long as it's kind of like double play in baseball, neighborhood play. As long as you're in the neighborhood around the 200 millisecond mark, move on. You don't have to go crazy saying, well, it's not exactly 200 milliseconds. It's 195 or 165. Close enough, move on. Okay? Same thing here. I have something to send, so I don't wait. I immediately send. So why was there a difference in where was the lost time coming from? I'm sorry?
Your timers.
Timers? No, what I mean is the application clearly said there's this missing gap. And when I went through this trace, I could account for every millisecond and every microsecond. So where's the discrepancy? Any ideas?
Transit time.
Transit time? Okay.
How big was the difference?
In actually, transit time is not and you're talking about a serialization delay.
How much delay were you looking for?
The budget that we were looking for, sometimes up to 200 milliseconds, sometimes 100 milliseconds per transactions, right? So these are hundreds of milliseconds that we have to account for. Clearly, it can't be serialization delay. Even on a T1, a full-size packet only takes 8.5 milliseconds to get through. So I need to somehow find hundreds of milliseconds to account for the discrepancy. Any clues about, if you're an application guy, where do you log? At the application level. So you say, here you go TCP, here's some data, I check off, look at the time, mark it. Time packet sent. Is it the time that the packet was sent? No. Why? It's sitting in the TCP buffer. Because Nagel says, try to hold on to the packet as long as you can. So there are other buffers at play, whether it's retransmission. Just because you said, here you go stack, please deliver this for me, and you mark that time, doesn't mean that that packet's not going to get lost, has to be retransmitted, or it got stuck in some buffer, in this case Nagel and delayed act. So the hundreds of milliseconds that we lost was because his timing was on the application level, not at the TCP socket level. And actually, just before there was a last bullet that said political correctness or diplomacy is in play. What do you tell the business that spent $200 logging system that may not be telling you the true story? That's a difficult conversation to have, right? And for that reason, we kind of went all out in doing additional analysis. Because the backstory to this that I didn't tell you is, when we told them about this, they said, impossible, can't be. They said, well, here's the packet trace. We looked at it, we followed it through, and we literally walked his source code and with packet trace and said, you're closing the buffer, here's the data, here's the data that you sent, here's the marker, we see it, he sent ABC, we see ABC in the packet. So he saw the light. He said, oh, I didn't know about this. So we told him to fix it, and then I got a phone call saying, I'm doing testing, and throughput is horrible. And thank God it's a testing system, because if it wasn't testing, I'd be fired. I said, what's going on? So we look at the packet trace, and he was flushing at a character level. So every character was sending a packet, and so obviously not a good idea. So we said, no, don't do that. When you're done, flush. When you're done with the whole transaction and buffer, then flush the buffer. Don't do it at a character at a time. Do it line at a time, or paragraph at a time, for lack of a better word. So when we did that, I realized, again, it's kind of a political football. A lot of monies were spent. Logging may not be accurate. How do you deliver the news? You dazzle them. And again, how do you dazzle them? Well, in this case, it was actually, I was more curious than anything else. And I did want to dazzle them, by the way. But so we took it an extra mile, and we did simulation studies. Because we also found, by the way, oh, I'm sorry, I didn't show you this. Again, this is a small sample I chopped out. Clearly, we see retransmissions, packets who are being lost. The exact packet loss rate that we tracked on the firewall, and it was a firewall in this case that was dropping the packet, but it was an old firewall, decrepit firewall, and it was dropping packets at a rate of about 0.7 or 0.7 or something like that. Very, very small number. We don't even flag on any alerting platform at that level. Okay? So then we got into the conversation of, we have to upgrade the firewall. They said, are you out of your mind? There's no packet loss, or hardly any. It doesn't justify it. I say, well, we see packet loss. That's the only place that I know it's getting lost there, because I put a sniffer before and after the firewall, and it got lost. There is no question. So I needed to prove impact. And when you get down to these small numbers, it's very hard for a human mind to. So I did something that I normally never do, and I created a pretty whiz-bang PowerPoint. And so Kristen, who was on my team at the time, and actually, before I get to that, actually, what happened when we fixed it, and here's the feel-good story. This chart represents all the trades that happen at a 0.5 seconds or less. You see a huge spike here. Before, this thing was all over the place, because delayed act kept coming in at random times, depending on whether I had 2 blocks of data to send, 1 block, etc. And this chart actually shows before and after. The yellow here, or the light color, is the number of trades that happened within less than 2.25 seconds before and after the change. So all of this was lost business, literally lost business, to tune of because of Nagel delayed act. And after we did the change, this happened, and then they went to algorithmic trading. And if they had gone to algorithmic trading with TCP, delayed act, and Nagel, we would have taken a bloodbath. Because algorithmic trading it's no longer humans. In this case, literally, a human had to look at a mouse, look at a screen, and OK the trade. Next pop-up comes, read it, OK it. So the 200 millisecond was not visible by anyone. But the minute you take that human moving the mouse over and clicking on OK, you take him out of the equation, and the systems are doing it at micro and millisecond time frame, 200 milliseconds, we would have taken a bloodbath, right? And again, this is what that represents. So what does this chart represent? Well, we did a network simulation study to see what would happen with that packet loss of 0.7%. And we use OpNet, and we replayed these packets in we recreated the network in OpNet, we loaded the packet traces, and we ran through it for a few hours. Because there was the dazzle factor that I had to do. I had to blame some other people besides, kind of throw the light away from the logging issue. And so I needed to kind of find root cause. And so one of the things they said, all right, let's do this network simulation study to see what impact it has. And what you see here is that at 0.2% packet loss, there's a smattering of blues up here. This is a transaction response time. These dots represent a trade that happened. Okay? And for the most part, it's completely hidden here, but almost all the blues happen down here. Okay? And again, this is before we fixed it, so the average time here is 4.5 to 5 seconds. Before that other chart that I showed you, trades were completing in 2.5 seconds. That's how much of an impact we made. But at this point in time, when there's packet loss, all the blues are down here and very few percent up here. When we went to 0.7% packet loss, look how many more pinks are here. Okay, and at 1%, forget about it. Look at all these yellows that happen here due to that small packet loss. And so we convinced both management and firewall and our design document to say, in a trading environment, 0.7% packet loss is unacceptable. Okay, so you have to go to Palo Altos of the world, Splats of the world, Junipers of the world that can do high packets per second throughput on a firewall. Okay, or because it's market data related, it's open. There's no security requirement per se. You go with a router-based ACL. Okay, and so when we did this study, again, this is what we showed here, and I actually deleted the wrong PowerPoint, so I can't show you. But I actually gave an animation of what Nagel does, which is, you know, you got this big pickup truck, and everybody's trying to load up these barrels one at a time, and you're doing the right thing. You want to maximize the time. And then they say, well, how do you fix this? I say, well, you don't have to necessarily use a big, huge truck. You can use a pickup truck, right? Make it smaller by decreasing MSS. So that's a hack. You can make the MSS smaller to trick TCP and delayed ACK into thinking, okay, I got 2 packets, they're full size, but that's a hack at best and not the right solution, but a solution, right? And once we did this simulation, we said, all right, let's take the time to fix your code, because this is all your impact right here. This is what's happening to you, both in terms of delayed ACK, because think about it, this is kind of plays on each other. You lose packets, you introduce more packets that can be caught in a delayed ACK scenario. Right? So you're compounding the problem. Okay? Any questions on that so far? No? Yes, a couple of questions. One.
Yeah, so what changes the behavior to use Nagel?
Okay, so yeah, how did we fix it?
So actually, because in the graph you showed that everything was working like fine, like there were no training. But
Oh, that's actually after the fix. So this is what the packet trace looks like after we fixed it, and you'll see a clear difference. Let me pull it up. So let's take a look at this packet trace, and we'll start down here. Right? We have some packet, a small size packet. We sent 4 bytes in this case, and he had something to send, so we get an immediate acknowledgement. We don't know yet at this point if we fixed anything, right? Because he had something to send. What do we need to see to make sure that we fixed the original problem? I'm sorry? Delta time, but we need to see what kind of acknowledgement? Naked acknowledgement. Okay, so let's look for it. So here's one. So I sent them a packet of 144. They acknowledged me in 5 milliseconds, even though he had no data to send. Right here is proof positive that delayed ACK was defeated. You can turn it off, for example. Both. And so one of the things that you see here is that even though I sent him a small packet that fixes my Nagel behavior, that doesn't necessarily account for his delayed ACK behavior, right? Because remember, it's 2 different concepts. Nagel, buffer as much as you can. Delayed ACK, don't acknowledge just a single packet. In this case, we said, no, acknowledge me. I don't care. And
you don't need that.
Yeah.
Because the ACK comes later, as long as Nagel.
No. The only problem is, so I know exactly what you're talking about. The only problem is when you have serialization in your processing. In other words, I can't send you the next packet until I get positive confirmation from you that you got it, right? So this is application level acknowledgement that it wants to see before sending you the next packet. In a bulk transfer type scenario, I don't care about delayed ACK. I don't really care about ACKs so long as you ACK me before my window runs out. Acknowledgements really don't play a whole lot of role in bulk transfers and case like that, because I'm sending you all this data, and if all your ACK except for the last one gets lost, I don't care, because acknowledgements are cumulative. The minute you give me an ACK, one ACK, I'm good. I know I'm good up to that point. The fact that I lost 15 ACKs before that, I could care less. In fact, I don't even know. There's no way to detect when an ACK gets lost. And in almost all cases, it doesn't matter if an ACK gets lost. And then, so what happens here? I get a packet here. This one was a naked ACK. He then immediately follows up with application delay. So there's nothing to freak out about. He spent some time cleaning house, sent some data to us. We immediately send something else. Again, we have the data. We send something. He immediately acts me back, naked ACK, right? So we know that now we defeated NAGLE delayed ACK. Simple problem, happens all the time, and it's horrific in a real-time TCP. So the moral of the story is, when you're doing real-time traffic, TCP is not the best, because TCP wasn't really meant to be this back and forth, fast shuttling protocol, right? It has congestion control, it has setup time, it has slow start. It has a lot of built-in mechanism, so typically TCP is the wrong thing to do. Okay? And you have to take, and if you have to use TCP, you have to take consideration, you have to take these conditions into consideration.
Is it only because the pieces you're sending is small? How about if you're trying to do real-time short hops, but you're sending big packets?
Yeah, so if you send 2 full-size packets, he would immediately acknowledge you.
So you're only dealing with this because you're sending little pieces?
That's right, and it so happens actually, and this is one of the examples. So here, this is an example of how Microsoft does it, and you can see here, let's see if we can find one. So even though 172.16, even though 172.16 sent me a 16-byte packet followed by 38-byte packet, I immediately acknowledge. That's like 300. There's a round trip here, right? So I'm looking at it from the wrong angle. But this is actually how Microsoft does it. Microsoft doesn't care if it's full-size packets or not. So long as I get 2, I will acknowledge you. All right? A lot of and in fact, last year, someone came up to me and said, "Why is it doing this?" And I said, "Well, it's a Unix system that says 2 full-size packet qualifies for an ACK, naked ACK." Okay? And he said, "How do you fix it?" Well, you have to turn it off or trick MSS, right? And sometimes those are not options that are available to you. Any questions before we wrap up?
I don't know if you're allowed to say, but in this case, the first use TCP was developed with conscious one.
I didn't.
The first use TCP was developed. Is that a conscious choice on their part?
That to use TCP or? No, they, yeah, well, because, and you can't really blame them, right? Ever since every computer science class that you take, they tell you what? TCP is reliable, UDP is unreliable. So if you're working with a trading floor, the first thing you say is, I'm not going to use an unreliable. It's a different concept. The word is actually bad, right? It's not that it's unreliable. It just means that you have to take care of the reliability, like TFTP does, right? So
how much does it work if the recipient of the packet takes it upon himself now to send back the subset of an ACK using TCP?
So the question is, how much worse is it if you...
Overhead-wise.
Oh, overhead? You get one 60-byte packet on your network. And in one case, I actually did that. And because it was a Linux kernel that could not reduce the delayed ACK timer, because oftentimes you can set the delayed ACK timer to be 10. And at least you reduce your penalty to 10 milliseconds before you send it. In this kernel, you cannot, and the sender couldn't send more. So we were in this delayed ACK. It was very annoying to us that we couldn't defeat this delayed ACK NAGLE problem, but we actually contacted Red Hat, and we're working with them to recompile, and it's a very sensitive platform, so it's not like, I'll go ahead and upgrade to this version, right? So we had to do pro services, and so sometimes, in most cases, the choices are make the MSS small, to force full-size packets, but then again, you're limiting yourself because you're now putting small packets on the wire. Or turn off delayed ACK, or decrease the timer if you have that luxury to say my delayed ACK, the most you're going to wait is 5-10 milliseconds. Okay? That's it actually. So, and this one I thought it was worth spending a little time, even though it's a simple problem, because I wanted to kind of walk you through how my team and I would sit down and go through these. And in the back of our, we're always thinking about the concept. So the one thing that I would recommend is that as you do protocol analysis, keep looking at traces. Your eye, sooner or later, will pick up on these different things over time. And the other thing is know TCP. A lot of people say, I know TCP, but you really need to know TCP. You need to know what it means to have a delayed ACK versus a naked ACK, what it means to have NAGLE, what it means to be full MSS, non-full MSS. Okay? So if you invest the time, and every time you get stuck, look something up, commit it to memory, and over time, you're going to just be able to instinctively know this is a delayed ACK because it's a naked ACK. All of these things will happen instantaneously and without having to think about it. Okay? So that's my advice. Yes, one more. Oh, so, okay, so, sure. So if we look at, let's follow, I don't know if there are multiple streams here or not. So, okay, so that's good. So this is another way to find out that you're being gated by something else. Nothing in nature has this type of frequency, or, right? So when you see this type of behavior where it's clockwork, right? Something is influencing the transmission and something inefficient. Because this is saying, I sent a packet, I had to wait a little bit, sent packet. I had to wait, sent the packet, sent the packet, wait, sent the packet, sent the packet, wait, right? So when you see this type of gated behavior, whether it's a sawtooth diagram or these exact stair step that repeats over and over and over, you have external factors at play. And these are easy to find. Why? Because this is happening all the time. So these patterns are actually easy to pick out. Okay? You just have to know where to look, or get lucky, like in the case with Citrix. Okay, any other questions? Okay, yes. I'm sorry, I can't speak. Yes. Problems like oh, okay. So the question is, I keep saying look for patterns. How often do you find problems or not find problems, right? I would say if I were to break it down and I open up a trace, by the time I do, that could have been bad. By the time I do this, and I do this, looking for sins, and by the time I do this, I sort by delta, come down, look for patterns, and immediately you see a pattern here, right? These are application level delays, 34, 34, 34. There are bunches of 200 or so delays here. They're all grouped. So the pattern isn't just about ordered number of packets, it's dissecting and putting the information the way you want to see it, and immediately I know this is a delayed ACK because I see these bunches of 200 millisecond, right? And I also know on my side it's about 90 some odd, or I see bunches of 90. So when you see this pattern always happening with a source of 192.168, delays of 90 milliseconds, right? I scroll down, I see around 200 milliseconds, followed by all the source being 10, I know I have a pattern. So by the time I do these 3 or 4 things, I would say 60 to 70% of the time, I have my problem. Or at least I know exactly where to go look and do a deep dive. Okay? And then the other one that I do again is, and you'll be surprised over time when you is this. I literally go down here and and this is real time. I do this in real time. And I would say, I don't know, 5-10% of the time, I stop and my brain or the eyes, something flashes by because as you do this, even though numbers are changing, your eye tunes it out automatically. Your brain tunes it out, and it will look at something that looks unusual, that breaks the pattern, and you stop and you look. Okay. The final thing I wanted to say was I always try to give something back. I can't do it with scripting or with Wireshark, so I do the presentation. But the one thing that I find useful, and again, email me, is I had my guys write a diff in Excel for router changes. So what it does is you type some commands, and as a pre-checkout commands that you want to type, and then within Excel, the telnet goes out and types those commands and sucks it into Excel. Then after the change, it'll do the same command and then line it up intelligently. So when the interfaces change and you're adding interface level commands, the following interfaces all line up, right? And things like when you do BGP checkouts, sequence numbers and database numbers, updates, I don't care about those. I do care about the prefix number column and the up-down status column and the neighbor column. So there's a regular expression engine built into that, so you can create your own intelligent diff. So if you're interested in seeing a diff that and again, the whole goal is at 2 in the morning, I don't want to see a Unix diff with brackets that jumble up my config. And so this one lines up all the interfaces and sections, ACLs all line up, etc. And it highlights sections turn red at the top when you check out commands. There's a difference. It turns red. You can click on it, go to that section, and do your checkout. So if you're interested in something like that, email me, and I'll shoot it out. Okay. Okay. I forgot to stop this.